Any other homeworks? Cool. All right, a number of things we want to do today. I want to start off by talking about Lab 2 and talking about where people lost points on Lab 2 to hopefully help you not lose points on Lab 3. And then we want to talk about switches and LEDs. This is something that you encounter in 120, but we're going to use switches in particular throughout this course, and you're going to use them throughout Engineering 270. And there's several ways to hook up switches, and some of them don't work at all. Some of them short out your power supply. Some of them kind of work, but sometimes start to fail. And exactly one way to hook them up works perfectly every time. So I want to go through how to hook up switches and make sure everybody is clear on that. And then I want to talk about homework 4, which I posted this morning, which is going to let you play around with designing with switches and LEDs, and also give you another round of doing circuit design, which was part of Lab 2 and will also be a part of all the labs we do. So we'll go over the homework, and then I want to talk about Lab 3. And Lab 3 I consider officially opens next Tuesday, and you have a week for that. So we're about a week and a half before it's due, but it's a really long lab. And a lot of the work is not done in the collaboratorium, it's done on paper. So I want to go over Lab 3 today to give you enough time to not have to rush through all the stuff that you need to do for that. And then we're going to go ahead and we're going to start talking about subtractors, muxers, demuxers, and some of these other things from Chapter 9. So Chapter 9 is kind of glommed onto the side of the course, but it deals with adders, multiplexers, some of these other functions. And then we'll come back and start talking more about propagation delays and glitches, and this will lead us eventually into sort of the second part of this course, which is dealing with machines that have memory. And that's where the course gets particularly interesting. So let me talk about Lab 2 first of all. So if you had it turned in as of yesterday, I graded it, and I'm giving you feedback in the PDF. I'm marking it up inside Canvas, so if you pull down a copy of that, you should see my notes in there. So the first thing is circuit diagrams. So experiment 1, you were taking an unknown IC and you were building a circuit, and you were connecting the inputs to ground or power to feed in ones or zeros. You made a truth table from that. You looked at the truth table, thought about it, and tried to figure out what the circuit was, right? So you're describing that in the lab report, and remember the goal is that somebody else can reproduce your work. So if you say something like, in this experiment we built a circuit using an unknown chip and made a truth table from it, and you show me the truth table, right? I have no idea where that truth table came from, because I don't know what circuit you used, right? And almost nobody put a circuit diagram in here. So how am I going to reproduce your experiment if I don't know what the circuit was? Right? Now if I know what the circuit is and I see it, and there's an input labeled A and another input labeled B, and your truth table has inputs labeled A and B, now I can do exactly what you did. I can set A and B to 0 by connecting those to ground. I can write 0, 0 on my truth table. I can look at the output, which is labeled, I don't know, X. And if there's an output X in my truth table, I can say if the LED was off, it's a 0. If it's on, it's a 1. But if your inputs are labeled A, B, and your truth table inputs are labeled X, Y, where did X and Y come from? Right? So I need to understand what you did by reading your lab report. Okay, that's what the lab report is doing. It's conveying to the reader what it is that you did. That's why we have things like procedure and all this stuff in there, so that somebody else can reproduce your work. So absolutely, you definitely need circuit diagrams. Okay. And a picture, you know, can be nice. Izad takes off points for pictures, I think, so warning if you take courses from him. I don't mind having, you know, photographs, but you've got to have a circuit diagram. right? Because that unambiguously tells you what chips were where, what was connected to what, where was power, where was ground, those kinds of things. Experiment 2, we did the same thing in experiment 1, but moved the wires from pin 1 and 2 to pins 3 and 4, right? Okay, that's a description of it. Put in the circuit diagram, right? Because that's completely unambiguous. Which wire did you move to pin 3? Which one did you move to pin 4? Right? So circuit diagrams tell you exactly what the circuit looks like. So that's the first thing on those experiments. So as far as the truth tables, here's what so I'll just call this X1 for experiment 1. And you wanted 3 separate truth tables, but I'm just saving on trees. So for experiment 1, what you should have found was a truth table like this. And some people found that, but a lot of people did not. And there's a number of things that can go wrong. For one, those unknown chips, sometimes it's hard to read the numbers on top and know which one is 1, which is 2, which is 3. So I think there was some switching around going on inadvertently. Secondly, connecting something to ground is not the same thing as leaving it disconnected. So if you have if you look at the original lab, right, so over here we've got input A and input B. So I suggested instead of having these switches, right, just use the wire. So if you have VCC put through a 1K resistor, if you connect a wire from this point here over to pin 4, that's putting in a logic 1. If you connect a wire to this point here, which is ground, over to pin 4, that's putting in a logic 0. If you don't connect pin 4 to anything, that's undefined. It's got to be fed either 5 volts or 0 volts. The reality is, for this type of chip, if you don't connect an input, usually it comes out as a logic 1. But don't ever rely on that, because as power supplies fluctuate, that can go away. So make sure you're always connected to either 5 volts through a resistor or directly to ground to put in a 1 or a 0. So I think in some cases people had inputs floating, and the effect is that your zeros are basically treated like 1s, and then you get a really unusual looking truth table. So this looks like an OR gate, which is a 74LS32, I think. Circuit 2 turns out to be an AND gate. And some people got that, some people got different things. And then circuit 3 is unusual, because you end up with something like this. And no, that doesn't look exactly like anything in the list of components, but here's what you can do. Try to simplify. Try to write an equation for X3 in terms of A and B. So where are the ones? 0, 0, and 1, 0. And cover that with a rectangle. And so the term corresponding to this, A could be 0 or 1, doesn't matter. B has to be a 0, so this is B bar. So the equation is X3 equals B bar. And there's your flash of insight. Oh, this is an inverter. This is taking input B and inverting it, and it's completely ignoring input A. And if you look at the diagram that was used for that, right, since this is an inverter, input 1 feeds output 2, which we're ignoring. Input 3 feeds output 4. So the output should be the inverse of input B, and that's what your equation for the truth table tells you is the case. So that's a 74LS04. So that's a tricky one, trickier. But again, if you don't know what the circuit is, there's no way that somebody's going to come up with an inverter by using, you know, this circuit or that circuit, or not knowing where to connect inputs A or B to. All right, experiment 4. The resistors in series and parallel. Got to show the circuit diagram, right? We took a series of resistors and connected them to a power supply and made some measurements, and then there's a table, V equals 5, I equals 5, right? How do I reproduce those? Got to know what the circuit was. What was the power supply set to? What was the size of the resistors, etc., etc., etc. And a picture like this, right, completely tells you, oh, you got 5 volts, you got two 1K resistors, the other end's connected to ground. Now you can take your own resistors, your own power supply, and build that yourself. And everybody was really good about saying that they measured the voltage and they calculated the current. That was awesome, right? That's really rare. So yeah, 5 volts was the measurement across the resistor, or 2.5 volts was measured across the resistor, and so on, and then the current calculated. And what you should find here, if you have something like this, is that across each resistor you get 2.5 volts. And for 3 resistors you get 1.667 volts. And the current is always your voltage divided by your resistance. So in this case it would be 2.5 over 1,000, so 2.5 milliamps across one resistor. If I tried to calculate the current across this resistor, it's still 2.5 over 1,000, 2.5 milliamps. Right, which is just confirming what we've heard, which is that in series the current's always going to be constant, doesn't change. But the voltage can change, right? If I had a different resistor here, I'd have a different voltage here. And guess what? These two voltages, they add up to 5 volts. That's part of Kirchhoff's voltage law. Currents add up, voltages add up. And so a general formula for N resistors, your voltage across one resistor would be 5 divided by N volts, and your current would be 5 divided by N milliamps. And then parallel, same thing. You've got parallel resistors. You've got to show the circuit. And since these are in parallel, each of these is going to be 5 volts. And it doesn't matter how many resistors you have, the voltage across any one resistor is always 5 volts. And the current through any one resistor is always 5 volts over the resistance, which is 5 milliamps. So your general formula for voltage across a resistor is just 5. And your general formula for current through one resistor is just 5 milliamps, and N doesn't factor into it. But notice what happens, since each of these has 5 milliamps, the total current is increasing. If I have 2 of these, I have a total of 10 milliamps flowing from 5 volts through these over to ground. And that makes sense because, right, these are pipes. The more pipes you have, the more water gets to flow through the pipes. If I have 1,000 of these things, I got a lot of ways for current to flow. There's going to be a big current flow from positive to ground. All right, and the numbers look good. That was really good. People's measurements seem to be right on in most cases. All right, traffic control signal system. So I went back and watched the video, and I spent 15 minutes at the end of the first half of class talking about logic design diagrams and the things that are needed for them. And I think I got one lab that had a logic design diagram with all the pieces in it. So you definitely need to show logic gates. Here's an AND gate, here's some inputs that goes through an OR gate, right? That's important, right? That's sort of the essential part of converting the equations into logic symbols. Okay, so that's a good step on the way, but you have to go further than that also to actually get all the points for this. So what we wanted was a diagram that included part numbers, right? And you already went through the website to find, do we have a 3-input OR gate? Well, no, but we've got some 2 inputs, and we can put those together. So you know which parts you're going to use. You specify that on the diagram, right? And then you got to specify pin numbers. So okay, well, this is coming from this chip, but which pin do I connect this wire to? Which pin do I connect that wire from? So part numbers, pin numbers, and then a component ID block, because, so let me redo this. So let's suppose you've got an AND gate, and here's A and B, and you've got another AND gate, and B goes through an inverter, and C, and then you're going to take these and put them through an OR gate, and that's going to be X. Okay, so that's a good first step, right? That logically shows you how your circuit is set up. What is an AND gate? It's a 74 LSOH, and that chip has 4 individual gates in it. I need 2 AND gates. I can take those both from a single 74 LSOH. So in my component ID block, I'm going to say, okay, there's a chip U1, that's a 74 LSOH, and this is going to come from U1, and this is going to come from U1. And U2 is going to be an inverter, that's a 74 LSO4, and that's where this inverter is going to come from, and so on. And you have your usual ground and power connections, and which pins have no connection, and so on. And now you put in pin numbers. Well, I can use any of the 4 AND gates inside this chip. So you go to the data sheet, you see where the inputs are, where the outputs are. Okay, I'm going to go in on 1 and 2 and come out on 3. And here I'll go in on 4 and 5 and come out in 6. And U2 is an inverter. Maybe I'll just go in 1, come out 2. And you do the same thing for your OR gate, right? And now you have what's called a wiring diagram. This is a diagram that you can forget everything you've done so far up to this point. You can forget the truth table, the equations, all of that. If you have this, you can build your physical circuit. Right? U1, go to your parts box, find 74 LSO8, put it in your board. U2, find that, put it in your board. Grab a handful of wires and a highlighter and say, okay, I need to connect pin 2 on U2 to pin 4 on U1. Go to your proto board, put a wire between those spots, and then maybe mark this line in a highlighter, maybe on a copy, right? And just do that until you've highlighted all the wires, and now you've got your circuit. All right, so experiment 5, draw the intersection, right? Saw lots of good intersections. System diagrams, saw system diagrams. Truth table. And I think everybody had a truth table. To go from a truth table to a circuit, you got to have equations, right? So in some cases, I saw the equations written over here, but write out those equations, and hopefully you're simplifying, right? A few people didn't simplify, and you get a very complex circuit. That's not wrong, but if you simplify, it makes things a little easier, or a lot easier in this case. So you'd show your K-maps or whatever algebra you're doing or something to get your simplified equations. And once you have your final equations, then you make the circuit diagram that corresponds to that. All right, and then the rest is conclusions, lessons learned, new experiment. Lots of cool new experiments. So is that pretty clear what I'm looking for? So the homework that I posted is going to basically be doing a start to finish circuit design, and we'll run through that after we talk about switches and LEDs. But it will be another chance to sketch out a circuit, and it's a fairly small circuit. It's not like millions of gates. There'll be a chance to do that, and it's double point homework. It's worth 20 points instead of 10. So because it takes a fair amount of writing. Yeah, make sure you indicate what ones and zeros mean when you're writing your system diagram. Here's inputs A, B, and C. That's a good place to say 0 means there's a car present, 1 means there's no car present, or whatever convention you're using. Because it's up to you, right? What kind of sensor you're going to use. You might have a sensor that generates a 0 when a car shows up. You might have a sensor that generates a 1 when a car shows up. Perfectly valid, but just let the reader know what type of sensor you're using, right? What's the 1, what's the 0 mean? Output 0 could mean green. 1 could mean red. Most of us tend to think 1 means go, green, 0 means stop, red, right? But that's just, for whatever reason. So specify it, because that's going to affect your truth table. Okay, we're going to see that in the homework. And the other thing, right, when you're doing this, make sure you think about what kind of chip U1 is, because inevitably someone will say this is U1, U2, U3, U4, and every gate will get a different U number on it. You don't really want to do that, because each of those U's is a physical chip, right? And if you need 4 OR gates, and you've got a chip that has 4 OR gates in it, you only need 1 OR chip, right? So each of those OR gates might be, U5, and you just use the pin numbers to say which of those OR gates are we using inside. So this is a picture of what you're going to actually physically wire. Yeah?
So if we were to reuse the gates, would we draw just like a much bigger AND or OR gate? Because there'd be multiple wires flowing into it, so would it be exceptionally large?
So no, not necessarily. So here's 2 AND gates. Oh, you mean a gate with multiple inputs?
No, I see. Now you're just like with a pin.
Yeah. Just use the pins to tell you which one. Yeah. All right. So new experiments. I'm going to give you some additional rules here for new experiments. Because I've seen good new experiments so far, but they're starting to overlap. And so we're going to eliminate some possibilities. So new experiment. Okay, no traffic light experiments. So no more variations on traffic light circuits. Okay, 4-way intersection, 5-way intersection, yellow lights, etc. Nothing to do with traffic lights. Okay. No experiments that involve creating new gates from old. Because we talked about how you can build anything with, say, a NOR gate, right? So there were some experiments with trying to make an exclusive OR out of a NOR and stuff like that. Those are cool. From Lab 3 forward, though, let's not use that one, because it's already been used by a bunch of people. And one more, no determining what voltage equals a 1 or a 0. Because I got about 5 new experiments on that, and I had one of them on Lab 1. So that one's tapped out. And no experiments measuring resistors in series or parallel. And I'm going to say in general, no experiments modulating things that we've already done as experiments. Okay, so I'm going to say no tweaks to old experiments. And it's a little gray what a tweak is. A minor tweak's probably not good. A major tweak, sure. And if you're not sure, you can shoot me an email and say, is this too much like an old experiment? And if it is, I'll maybe suggest something to turn it into a less subtle tweak. All right, so main thing for Lab 3 to get more points, right? keep going back to this idea, is there enough in my report for somebody to reproduce what I've done? Right? Forget everything that you know about the lab, just look at the report and say, if this was all I had, if someone handed me this and said, we'd like you to repeat these experiments yourself, is there enough information here to do that? Okay, that's really the test. Questions about that? All right, yeah.
So to clarify, when you ask us to make a logic design and a circuit design, you're asking us to do two different things.
Are you looking ahead?
Yeah.
Lab 3?
Homework 4.
Homework 4?
Yeah.
Oh.
Let's sketch a circuit for 1A.
Um, 1A. 1B, draw a system. No, which one are you looking at?
I'm looking at 1A.
1A.
With a sketch a circuit with a NO switch.
Yes. Right. So yeah, I'm gonna fill in the details on this, but yeah, that's just a switch, resistors, and power connections. So that's not going to have chips or pin numbers or things like that. But when we get down here to 5, draw a circuit, right? But I specify in here part numbers, pin numbers, etc.
Okay.
So yeah, those are different things. You're right. All right, but we'll go through this after we talk about switches. So other questions? All right, let's talk about switches. I should have brought in some switches. Actually, I have a switch. All right, here's a cool little box I'm making. And it has a switch. I can take out. All right, and I'll pass this around. It's a push button switch. It's got 2 leads on the bottom, and it's got a plastic button on top that you can push down. So what do you think happens when you push the button? What changes? What happens with those 2 leads when the button gets pressed? Completes the circuit. Any other ideas? So here's my really mediocre drawing of a push button. And it's got some threads on it. And it's got a lead down here. And it's got this looks like a weird creature now. And it's got 2 leads down there. And you know, you take this and you solder a wire into it and do something, and you take that and you solder a wire into it, and this thing gets to push down. It turns out with that switch, if you do not push the button, these 2 leads are electrically connected. And when you push the button, these 2 leads get disconnected electrically. It's a different kind of switch. So this kind of switch is called normally closed. And let me label these 2 leads A and B. So if the button is unpressed, then A and B are connected. And if the button is pressed, then A and B are disconnected. And this is just called NC, normally closed. Closed is the same as connected. And open is the same as disconnected. So that's kind of a weird button. There's a different version which is normally open. NO. And if it's unpressed, then it's open or disconnected. And if you press it, then it gets closed. And that's the type of switch we're normally more familiar with. You push it to make something happen. So normally open switches. The switches we use in this course for the most part are those little slide switches or rocker switches. They don't really have a push or don't push kind of thing. They're either in one position or another. But they use the same terminology, open, closed. So here's the top of one of these switches, and it's got 8 little slides, and there's some little piece of plastic sticking up, and you can slide in one direction or another. And usually one side of this is labeled like open. And it means if you slide the piece of plastic down here to the side that says open, the circuit is disconnected. And if you slide it up, then it's not open, it's closed, and it's connected. If it's a rocker switch, if you push down the side that says open, then it's disconnected. The other side is closed or connected. So when you start messing with these switches, a suggestion is get a multimeter, put the switch in your proto board, hook some wires on either side, hook those up to your multimeter, put it on resistance, and confirm what happens when you flip the switch. Right? Because that's going to mean a whole lot more than any explanation I give you here. One position, the resistance is going to be 0. The other position, the resistance will be infinite. And it'll show some kind of error message on the display of the multimeter. Right, so make sure you know what those two positions are. So how do we draw pictures of this? We usually represent these switches like this. And it's a throwback to the idea of a push button, right? This is what the button pushes down on. This is sort of normally open. And when you push the button down, this arrow comes down and makes contact with this side of the metal, and now this point and this point are connected. So in this position, these two ends are disconnected. When you push this down, they're connected. But normally open push button, normally closed push button, sliders, rockers, lots of different ways to implement this. Incidentally, you don't really need this for this course, but you need it for life in general. This is called an SPST switch, single pole, single throw. And it means a throw is a switch. It means there's one switch and it's got one point that it can connect or disconnect from. That's the only switch we deal with in here. But if you're buying switches on Amazon, you'll see SPDT, you'll see DPST, you'll see DPDT, double pole, double throw. And it's just more complex versions of this. So this is an SPST switch. Well, we have a bit of an issue, which is that when we're building circuits, we'd like to be able to do something like this. Have a switch that either feeds 5 volts, logic 1, or 0 volts, logic 0. And if we had a switch that you could move between 2 points, we could implement this circuit as it sees, as we see it here. Right, so that's a double pole single throw switch. We don't have those. All we got is a switch that either closes or opens, not a switch that connects the input to one of 2 points. So we have to fake that. So here's how we wire up a switch. So here's the line going to the circuit. And here's our switch that can either close or open. And a first idea would be just connect this point here to 5 volts. And And now if I close this switch, I got 5 volts going to my circuit. But if I open my switch, my input to my circuit is not connected to anything. Remember, that's not the same as 0. So we do something pretty weird. At the point that goes into the circuit, we put a 1K resistor, and we connect the other end of the resistor to 5 volts. So if I don't do anything with the switch, I've got 5 volts going into my circuit. That's a logic 1. Now I put a switch here and I take the other end of the switch and I tie it to ground. And now if I close this switch, if I bring that switch down, my input to my circuit is connected to ground, that's 0. So now I'm feeding a logic 0 in. This point up here is still 5 volts. That's hardwired to my power supply. But I have a 1K resistor between there and this point. So this is just like, you know, experiment 4, part 1 from the last lab. 5 volts, 1K resistor, ground. This will drop 5 volts over here. This will still be a logic level 0. So this is the way to build switches to feed inputs to circuits. In this course in 270. Okay, take the input to your circuit, first pull it to 5 volts through a 1K resistor, and then make a switch that will pull that input down to ground. And there are a lot of ways to try to do this that are not right. All right. So for example, if you leave off this resistor, because it's just a resistor, who cares, right? If you leave off this resistor, what happens when you close the switch? If you just put a wire here instead. You've got a short. You've got a direct path from power to ground. That's when your power supply makes that little clicking noise and the red light comes on. Because it's trying to pull infinite current, right? And the circuitry inside is saying, no, you can't do that. So that won't work. If you put the resistor over here, that will kind of work, but it could damage your circuitry. Because you have 5 volts with no resistor going into your circuit, theoretically that's infinite current. For a 74LS04 chip, that's fine. For a PIC processor that you use in Engineering 270, that might damage the inputs eventually. For an Intel X-Scale processor that costs $100 or so, that will totally blow the input pin. And then you have to remember, don't use that input pin again because it doesn't work. So we always want a 1K resistor if we're putting 5 volts into a circuit. And if you hook your circuit up to this point, it's always going to be at ground. And if you hook your circuit up to this point, it's always going to be at 5 volts plus a high current. And there's lots of ways that this can get wired. And like I say, most of them don't work, or they kind of work, but it's a question of luck. Or they might damage the circuit. This way is guaranteed to work correctly every time. And you'll be doing this in homework 4. So you get some practice at it. But every lab you do in 270, you're going to be building switches to feed circuits. So you get a lot of practice on this.
Is that called a pull-up resistor?
Yes, exactly. This is called a pull-up resistor. Because if you don't have this here, you've got either ground or you've got a floating input. What this is doing is saying, if you don't pull this to ground, let's pull it up to 5 volts. So that's a pull-up, and some like microprocessors, you can enable a pull-up internally through software. You can say, I'd like you to pull that up if I don't short it out to ground, and it'll take care of that for you.
I've also learned about pull-downs. Are we going to do anything with pull-downs?
Pull-down is the same idea. You could have this normally connected high and
Okay.
yeah. Yeah, remember that in 270 when they talk about port B. Because you can turn on pull-ups. All right, so that's the input side. That's how we're going to feed things into our circuit. We can do this, right? We can just connect a wire to VCC through a resistor or connect it to ground. But it's, you know, the more you move wires around, the greater chance you're either going to accidentally short something or pull out another wire by mistake or something. So if you make your switches and you put them over on one side of your proto board where they're kind of out of the way of everything else, and you get a nice dull pencil, you can flip the switches with that. and it's theoretically a more convenient way to set inputs. So that's the input side. The other question is output. So we have something coming from our circuit, and we'd like to know what the voltage level is. Is it a logic 1 or 0? You can hook up a multimeter, but if you have multiple inputs, that's kind of a pain. So we use these LEDs, right? And an LED, I draw it like this. And theoretically, we can take the other end of the LED and connect it to ground, and that may work or it may destroy the LED, depending on how much current can come out of this circuit at this point, because these can only handle a little bit of current. And if I were to hook this up to, say, a high volt power supply, run it through an LED to ground, it'll flash and pop and it's done, because it got too much current. So to make sure we never get too much current, we throw a 1K resistor here in series. And even if this is 5 volts coming straight out of Hoover Dam, guaranteed we'll never get more than 5 milliamps flowing through our LED. That's what the resistor does.
So why are we putting the resistor after?
You can put it after or before.
Okay.
Good question, but remember, current is supposed to be the same in a series circuit. So it shouldn't make any difference. You can do it wherever you like, as long as it's somewhere in that path. Let me see if I can find something without looking too hard. Actually, let's go ahead and do a 5-minute break. And I'll find you some LED pictures, and then we'll talk about homework 4. So go ahead and stretch your legs for 5 minutes.